Hello, this is Mike back with another Fusion validation model. Today we're going to do something a little bit different from the other prior validation models that we've looked at today. We are going to do a hollow cylinder with thick walls and a temperature gradient. It is a Rourke and Young example. And so we're going to do a thermal stress model. And to this point, everything that we've done is either linear static stress. I think we've done maybe a modal analysis or two. But we're going to get into thermal stress today, which is kind of cool. As far as the description is concerned, we are going to have a model that has an outside radius of 2 inch, inside radius of 1 inch. The height is 4 inch, and the temperature difference is 10 degrees Fahrenheit hotter on the inside. Now, the material properties are typical to what we have used a number of times in the past, and that Poisson's ratio is going to be 0.3, Young's modulus 30E6. What's a little bit different here, because it's a thermal stress model, we do need to specify a thermal coefficient of expansion. And in this case, it's 6e to the minus 6, and it will be a quarter symmetry model. And then we'll take a look at our stress tensors. We want to find the hoop stress, and we should see a 998 on the outer and a negative 1574 on the inner surface. And we'll compare those, the results that we get with those values, and see how far off we are. Two things before we start. And I already have my Fusion 360 launched here. It's probably a good time for me to check the about box. Remember, the versions do change, just so you know what version I'm working with in case you are using something different. So I have 2.0.11186 currently. The other thing I'm going to point out is a couple things in the documentation. So let me go to the question mark, the help again. We're going to go into learning and documentation. And then from learning and documentation, I'm going to pull up the product documentation. Now, in the product documentation, we can scroll down until we find the simulation category. And underneath the simulation portion of the help, of course, Fusion does a lot of things, right? There's generative design, there's drawings, there's rendering, and so on. So we're going to go into the simulation section. And underneath there, the first thing I'm going to take a look at is the how-to and expand this. I've mentioned this a couple times. The documentation's pretty good to explain, but I just wanted to show you where it was. So if I go to how-to, and then I expand the apply materials, underneath there is the ability to manage libraries and add new or custom simulation materials. So because this is a material with very specific properties, I have already created my own material for it. But if you click on that topic right here, there's the steps, add new or custom simulation materials. And this walks you through how to generate your own custom material. So you can create your own material, give it that 30E6.3 and 6E minus 6 on the thermal expansion coefficient. There's also a couple YouTube videos I've seen out there that also walk through the steps. That's why I'm resistant to do it myself. I just don't want to, replicate, what somebody else has already put out there. So I think the documentation is pretty good to follow. You could also, like I said, find a YouTube document on it. The other thing that I want to show you underneath the simulation category, if we come down to the reference category, underneath reference, there are accuracy verification examples that exist for Fusion. And if I expand that, we can see there are some different categories: static stress, modal frequency, structural buckling. So today we're doing a thermal stress, and in fact, there is a model that is basically the same thing here. So this gives you, if you do need to reference the dimensions or anything, this gives you the setup. So you can see outside radius of 2, inside radius of 1. We're going to do the same thing, height of 4 inches. Again, it'll be a thermal stress. I will follow this mesh size. The default mesh is coarse. You'll see parabolic elements. And the only thing I'm going to change here is a couple things, two things. One, they utilize the frictionless constraint. Because it is a symmetric model, I'm going to stick with the way that I've been setting up symmetry models, and that is to constrain the out-of-plane translation. And the second thing is they utilized a -10 on the inner face or the inside surface. Um, I'm going to use a positive 10 degrees. We're going to get the same hoop stress. It's just a matter of I'm following what was defined in the Rourke example. But whether you go with a -10 or a 10, you should get the same thing. So let's go ahead and set up this model. It is a simple model to construct, so I thought I would do that. We want the z-axis to be the axis of our cylinder, so I'm going to sketch on the xy plane, and we'll sketch a circle starting at the origin, just going out a little bit, and another one. And then let's go ahead and add in our dimensions. So the inside radius was a 1 inch or diameter of 2, and then the outside was a radius of 2 or a diameter of 4. And then from there, I can just add in a couple lines going from the origin, one vertical, and again from the origin, one in the horizontal. So that way I can then trim, whoops, there's the trim command, trim away the portions of this model that I don't need. And we're just about done creating the geometry. Just gonna, well, I want to extrude that. And what did we say the height of that was? I believe that's 4 inch. There we go. All right, so that's the construction of our model. Let me go ahead and save it. And this is validation 11. And it's a demo. So we'll save it as V11 demo. And then we're going to go into simulation. And as I toggle to the simulation environment, as we go into simulation, note the other analysis or study types, and for this one we do want it to be a thermal stress. So again, first time I'm getting into this analysis type for the validation models. So as we go in, make sure you choose the thermal stress, and we'll say create study. What happens if you don't? What if you already jumped in, you were following along and you jumped in as a static stress model? From the manage pull down menu, you can go into settings. So manage settings, and there right across the top is your study type. So you can always change the study type right there. So we're going to run with it as a thermal stress. While I'm in here, since I am doing a thermal stress analysis, this is where your stress-free reference temperature is defined. So it's currently set to roughly ambient or room temperature at 68 Fahrenheit. I'm going to change that to 0 degrees Fahrenheit. That's just, so you can determine a delta T. If we were to say this model were all at 100 degrees Fahrenheit, and then with whatever I set my stress-free reference temperature at, the delta T between those two, or the temperature difference between those two, becomes the delta T in my model, so that we can figure out the expansion based on the thermal coefficient of expansion. So again, that was under manage, and then settings. One, you can set the study type if you need to, and then second, you can specify what the stress-free reference temperature is. We'll say OK to that. All right, so then the materials, like usual, I'm going to go into study materials, and I usually change to my own library when we're doing something with a modulus of 36 and Poissons of 0.3. So the material I've frequently used, if you've been watching the videos, is this A3630E6. And if you click on View Properties, or I click on View Properties, you'll see that material had a Poissons of 0.3. It had the Young's modulus correct, but the thermal coefficient of expansion was a little bit off. And that's because I took this I made a copy of the A36 material that's in the library, and I had modified Young's modulus and Poissons ratio. So what I ended up doing for this material was just making a copy of my A3630E6, and I renamed it. So you can see I named it 30E6.36E-6. So I just gave it a descriptive name of what the modulus, the Poissons, and the thermal coefficient of expansion are, and I modified those properties, of course. So there's my 30E6, there's my 0.3, and there's the 6E-6. And again, if you don't have your own custom material, that's why I showed you under the documentation, those help steps exist so that you can create that. So I'm going to go ahead and say OK to that. And next, we do need to have some constraints. So I'm going to do a constraint, And like always, I'm going to use symmetry constraints. So this, well, that is to say when we have a symmetric model. So in this case, vector perpendicular here is the y, so I'm going to uncheck ux and uz. Rotate the model around a little bit. Go to constraints, this face right here, vector perpendicular is ux. So I'm going to uncheck y and z. And then lastly, on the bottom surface here, right there, that one is z. So uncheck ux and uy. All right, so that's it for the constraints. We do need to have the temperature loads on it. So because we are in a thermal stress, notice the loads. You have the two different loads here. You can go into structural loads or you can go into thermal loads. From the pull down menu, you can access those two as well. This one doesn't have any structural loads. It's purely going to be thermal loads. So we'll go thermal loads, and I'm going to select that inside surface. And for the inside surface, I'm going to do 10 degrees Fahrenheit. Keep in mind that if you're following that validation example or accuracy verification in documentation, they use a -10, so they do a colder temperature on the inside. But again, shouldn't make any difference whether you go 10 or -10 to the hoop stress results. Of course, for your deflections, yes. Let me go ahead and say OK to that. And then on the outside surface of this, we're going to add a thermal load right there, and that's going to be 0 degrees Fahrenheit. All right, so let's go ahead and generate the mesh. I'm going to right-click there and say Generate Mesh, and you'll see here why we're going to go with a finer mesh. You can see the default's pretty coarse for this geometry. We only get 2 elements through the thickness, which when we're looking at a temperature gradient through the model, basically what is causing the stress in our model and displacements in our model, it would be good to have a few elements through the thickness. So I'm going to go ahead and follow the pre-existing validation model in that regard. We'll go with an absolute mesh size, and we'll say that that is 0.2. We'll say OK, and we can generate the mesh again. So now that we have the mesh generated, a couple elements through the thickness, last thing that we need to do before we can interrogate the results is to solve it. So from the Solve pull-down menu, I'm just going to say Solve, and we'll run this one locally. Does not take very long. Once we get into the results, what we're going to do is on this XZ plane, at the inside surface and the outside surface, we will interrogate the results that we get at those locations for the Y stress tensor. So that way, that would be the equivalent of the hoop stress on this model. I'm trying to rotate it around so you can see the Y-axis here a little bit. Maybe if I go like this. There we go. So you can see the Y direction is off this way and off this way. So again, we're going to look at the Y tensor at this location and that location there. And I also am going to turn off the deformation on the model. So right from the deformation panel, we can turn that off. All right, let's go with, we want stress, not displacement, stress. And we're going to take a look at the normal Y direction. So there we go. And again, specifically, I want this corner and this corner. So the way that we can get precisely those points is to use the Inspect menu. And we can say that we want to create point probes. So with the point probe, let me go ahead and click a point here. There we go. And I want it to be precise. So I know that the dimensions of that should be 1 in the X, or the coordinates should be 1 in the X, 0 in the Y, 0 in the Z. We'll say OK. So there's one of them. And then the other one, Inspect, create probe point. I'm going to come close to that corner. And again, that was a 2-inch radius, so that would be 2 in the X, 0 Y, 0 Z. Say OK. All right, so there's our two values. And from that point, we can bring our spreadsheet over. So inside surface, I got a minus 1587. So inner surface, the theoretical value is 1574, negative 1574. So let's plug that in, minus 1587 we got from our analysis. So we are nicely less than 1% different there. And if we check the outside surface, again, theory was 998, our value is 1009, and we're right about 1.1%. So I think very good agreement with what the hand calcs are for this model. I like that one a lot, and hopefully you learned something from it, and thanks for watching. You have a great day.